Hi everybody, this is Amy and Annalie, back again to talk about basic chemistry for anatomy and physiology. We're going to talk about some chemistry in this class, and there are certainly pieces of it that we need to really understand as we talk about physiology in particular. If you ever find yourself wanting to know more details about the chemistry, a general biology course might be great for you, a chemistry course, and this would really be necessary if you were taking a 200 level A&P class. But for this 100 level A&P class, we're going to start with just the basics that we need to know to make sure that you understand all of the physiology that we need to talk about this semester. So let's go ahead and jump in. If you take a look at this, this is a picture of the periodic table. Hopefully you guys have seen this before. Here you have a list of all the different elements that are found in nature. Remember when we went over our discussion about the different organizational levels that are found in our bodies? The very smallest level that we talked about was called the chemical, or specifically the anatomical level. So each of these atoms really represents the smallest unit that we have in our bodies. Here's nitrogen, oxygen, hydrogen, and these are all found in many different combinations of our body and are found to make many, many larger molecules. So I just wanted to show you this picture so you know the chemistry that we're starting with, but we're going to jump into the pieces that we need to discuss. Practically speaking, for our class, we're going to be talking mostly about molecules and compounds, which really are a combination of two or more of those atoms that we saw on the previous slide with the periodic table. Some of these examples might be oxygen, up here, which is the air that we inhale. This is what provides what we have to send to all of our body cells so that they can function. Carbon dioxide is the compound that we exhale, that we expire, that's a waste product. Water, H2O, is the primary component of everything in our body, and this is made of 2 hydrogens and 1 oxygen. And then here's an example too of another compound. This is sodium chloride, and that's just really table salt. However, we see both sodium and chloride and many other molecules that are necessary for physiology, especially as it relates to the muscular system and as it relates to the nervous system. So let's keep going here. Let's start with water. This is a major compound in our body, a very important one. Let me get to my pen here so I can draw some things for you. We said already that water is made up of 2 hydrogen atoms and 1 oxygen, and you can see those here. Here's the hydrogen, and here's the other hydrogen, and here's the oxygen. One of the really important things about water as it relates to our body is that water has an electrical charge to it. So what you can see in this diagram is that the 2 hydrogens have a positive charge, or slightly positive charge, and the oxygen has a negative charge. What that ends up meaning is that water as a whole is electrically charged, and we would say that that would be considered polar. Polar, if you think about it this way, if we said that our classroom or a group of people was polarized on a particular, say, political topic, what that would mean would be that some of the class was on one side, agreeing with one particular idea, and some of the class would be on the totally opposite side, agreeing with the opposite idea. That's the same case here as it relates to electrical charge. We have a negative area on one side and a positive area on another side. So if something is polar, we could say that it is charged. Another good way to think about that is that if there's a group of people that's really polarized on a particular issue, you might say that there's a really strong charge, that the conversation was really highly charged, meaning that everybody was very divided on how they felt about that topic. So maybe that'll help you remember that too. The opposite of polar would be nonpolar, and that just means that everything is equally charged Or maybe a better way to think about it is that there is an even distribution of charge. See, in water we have the positive on one side and over here and the negative on the other side. If something is nonpolar, that means that there is an equal distribution of these charged particles in that particular molecule. So the important part to remember for this class is that water is polar. It has a charge to it. Now, one of the things that's important about water having a charge is that there can be other compounds, such as the sodium chloride that we talked about earlier. In some ways, when the sodium and the chlorine come together, they end up transferring some of their charge one to the other. And that's part of the chemistry class that we're not going to talk about much in here. But what I just want to show you about that is that because water is charged, water is actually able to separate particular atoms that were normally bound together and attracted by opposite charges. You see how the chlorine has a negative charge and the sodium here has a positive charge? Well, normally those opposite charges attract, and that sodium chloride would stick together and create a cluster of crystals, which end up being the crystals that you see when you shake some salt out of a salt shaker. So the sodium and the chloride create these crystals that stick tightly together. Well, when you add water to that scenario, or when you add the salt to water, those charged areas of water that we talked about, the negative and the positive, cluster around the opposite charges that they can find in the salt. And what happens is that the water actually separates these two molecules from each other. The chlorine and the sodium get pulled apart because of the water surrounding it as those like charges attract each other. This is what ends up happening when salt dissolves in water. The water is actually separating the sodium and the chlorine from one another. What this ends up doing is creating, instead of having a combination of sodium chloride together, we end up adding water to the scenario, like we talked about, and you split the sodium and the chlorine apart. These are referred to as ions. Ions are molecules or atoms that have a specific charge on them, and that always is going to happen when these molecules get separated by water. The reason this is really important for us is that our body is made, or particularly our body fluids, are made primarily of water. So we have lots and lots of these molecules here that have been split apart by water, and that means that we end up with lots of ions, individually charged particles, floating around in our blood and in our body fluids. These ions are also referred to as electrolytes. You might have heard that term more often, especially if you're thinking about exercise, if you're thinking about replenishing your electrolytes with something like Gatorade. The reason is that these ions, like the sodium and the chlorine, are really important for muscle contractions and for nerve impulse transmission. So we take a molecule that's stuck together, we mix it with water, and because of the charges, these two molecules get pulled apart, and because they retain their charge, they're referred to as ions. Alright, we just talked about ions and how they are charged particles. We also talked about how water has a charge as well. And because of that, we need to introduce a couple of new terms. Let me get my highlighter back for everybody. Here we go. There are a couple of terms that let us know how something is going to actually interact with water. So let me describe those to you. If you have a molecule that has an electrical charge, okay, like that sodium chloride, or even the water itself, that is considered to be a polar molecule. And because it is polar, we know that it's going to interact with water because those charges want to contact one another. So the term that we use for things that are polar or charged is hydrophilic. That means that they love water, or they interact with water. On the other hand, remember we talked about some molecules who have an even distribution of charge. Those would be considered neutral molecules, or they have no overall charge. And those molecules are called nonpolar. Nonpolar molecules do not like to interact with water at all. They don't have any charges themselves that are attracted to the charges on water, and so what they actually do is that they try to hide from the water. So that's referred to as hydrophobic, or afraid of water. You've probably all seen the example of water and oil trying to mix the two together. If you haven't, go ahead and try that at home. That's always a good thing to play around with, especially if you have kiddos around. But in this example, this cup is filled with water here, but oil has been added, and you can see how the oil and the water do not mix. This oil is nonpolar. Let me get my pen again. The oil is nonpolar. Remember we said that that was going to be no charge particularly, and the water is very polar because it has all the positive and negative charges on it. So this water section never mixes with the oil. The reason this is an important topic for our class is that, remember we said that all of our body fluids are made mostly of water. And there are quite a few things that need to be in our body that are considered to be nonpolar. They have more of the characteristics of oils or fats. And because of that, those molecules are going to have a more difficult time being transported through the water of our body fluids, the water of our blood, and they're going to actually require special transport, potentially. They're going to behave differently than something would that's polar. So we'll come back to this idea quite a bit about characterizing particular molecules as polar or nonpolar. But just remember that polar molecules are charged, nonpolar molecules are non-charged, or they have simply an even distribution of charges. And because of that, the nonpolar molecules are going to stay separated from water, or they're going to want to try to stay separated from water as much as they can. Hope you have a good time thinking through this. This is an interesting thing to try out. You can even try at home, take some food coloring, and you'll be able to see whether or not that food coloring is polar or nonpolar based on which layer of this particular experiment that the food coloring ends up sticking in. So the food coloring will either color the oil section or it will color the water section, and that will tell you if that food coloring is polar or nonpolar. If you have any questions, please let me know at any time, and I will be back again to talk about some more chemistry.